All right, in the previous video in correlation regression, we looked at simple just correlation between two variables, which again just simply looks at the relationship, not directional, but just how do the two variables relate to one another. And we looked at simple linear regression. Simple linear regression always just involves one what we call independent variable or predictor or influencer variable and one outcome or dependent variable. And there we are looking at directionality. Does the independent variable predict or influence the dependent variable or outcome? In those cases, we run it. We can see what percent of the variability in the outcome can be explained by that one independent variable. We can look at what's called the regression coefficient to see how that variable is related and whether it's significant or not. But sometimes you may be in the situation where you're interested in more than one variable predicting an outcome. So in our examples in the previous video, we looked at GPA separately predicting the final exam score for students and their math anxiety score predicting their final. But what if I had a model, I had done some lit review and wanted to know how do those both together predict somebody's final exam score? So maybe we know that students, but the research shows us that students who are more academically capable are going to do better in statistics. Those who tend to struggle with anxiety in math are going to struggle, and we want to know if we have that data on students, both their GPA and a score on math anxiety, how well can we predict how they're going to perform on their final exam? In that case, we can't do simple linear regression because linear regression only involves one variable. And so we need to run what's called multiple regression. So I'm going to quickly show you that, and then I'm going to show you one other thing related to some scatter plots, which helps you to look at the relationships between variables to make sure they're actually linear so that you can actually use either simple linear regression or multiple regression. So in this case, I'm going to go back to analyze, back to regression, back to linear. Again, our dependent variable is still the score on the final exam. That's the outcome we want to predict. In this case, I had this in there before, but I can take it out of there. GPA is one of the variables we want to know. Does it predict? And we also want to know the math anxiety. So I can put them both in there. So in this case, it's going to run a model that looks at both of those together as predictors, predicting the single outcome. Again, we call that multiple regression. I'm going to hit OK. Now you can see the output looks the same, but here it tells you there were two variables entered, the math anxiety score and GPA. Your dependent variable or outcome is the final exam score. We have the same statistics. In this case, the R squared is 0.371. What does that mean? That means 37% of the variability in the outcome on final exam scores in this sample can be predicted by or explained by someone's score on a test of math anxiety and their GPA. So if you remember from the previous examples, I think our R squared was a bit smaller than that. So we've added predictive power. We've gotten better at predicting by using two variables. Again, we drop down to where it says ANOVA here, and this F statistic and significance value tells us whether the model overall is significant. In this case, it's below 0.05, so we say that it's significant. What does that mean? It means that a model predicting final exam score that includes the independent variables of math anxiety and GPA is significant. It explains a significant amount of variability. In this case, about 37%. And then finally, we're going to drop down here that these coefficient tables looks very similar. It's still got the constant. What does that mean? This means this would be the final exam score if GPA was 0 and the test of math anxiety score was 0. We know we don't have such a thing, so that value doesn't really mean anything, but that's just the constant score. And then our constant value, in this case, rather than just one regression coefficient, we now have two. We have one for GPA and one for math anxiety. Again, what does this mean? We have 14.746. We come over here. It's a significant predictor. We look down here, score of test on math anxiety, negative 0.526. Significant. So both of these are, the model overall is significant, and each of these individually is a significant predictor. Now, a quick caveat about interpretation. You can't do the same thing as you did with simple linear regression and just say, this means that for every 1 point increase in grade point, we would expect their final exam score to go up 14, 0.74 because we have this other variable. So what we have to say is holding math anxiety value constant or accounting for the math anxiety. For every 1 point increase in GPA, we would predict that a student's final exam score would be increased by 14.746 points or 0.442 standard deviation units. Similarly, if we want to interpret this, we would say holding GPA constant or accounting for a student's GPA for every 1 point increase on their score of math anxiety. Again, remember higher is more math anxiety. We would expect their final exam score to drop 0.526 points or negative 0.332 standard deviation units. So not surprising, as math anxiety goes up, we're expecting a bit of a drop in final exam score. So if I was reporting this, I would say the multiple regression of predicting final exam score from math anxiety to GPA was significant, accounting for 37.1% of the variance, or R squared equals 0.371. And I would report the GPA coefficient was 14.746. I could report the significance value. The math anxiety coefficient was negative 0.526. Report that it was also significant. Both of these were significant predictors of final exam score. All right, so that's generally how to run it. One other quick thing that you do need to do is remember this is called linear regression. Linear obviously refers to a line. So you have to make sure that the relationship between the variables actually is linear in nature. And so to do that, you can just simply run what we call a scatter plot. So I'm going to drop down here, graph scatter, and you're going to get something that looks like this. So for example, let's say my outcome, we already said our outcome is the final exam score. Let's say our GPA is this x-axis. Actually, let's use the anxiety. And I hit OK. And you get a little diagram that shows what the variables look like, or what the scores. Each one of these dots represents somebody's score on math anxiety and their score on the final exam. What you're looking for is a linear relationship. One quick way to do that is if you double click on it and you go up to where it says add a fit line. Actually, not add a fit line. You're actually going up to oh, no, there we go. That's right. Sorry about that. So it added, you can see there it added this line. So if you're going to try to draw a line through the data, let me get out of that now. Let me get back into where my data is. You can see that it drew a line, kind of try to evenly space through the data. So we have an even amount up here and down there. And you can see that it is a line. It is a straight line. There are occasions where you might have data that might look like, if you were to try to draw a line through it, would actually be more like a U-shaped or maybe a inverted U. That is not a linear relationship. That is a curvilinear relationship. So you need to make sure, even though it doesn't look perfectly like a line here, if you were just to look at the blue dots here, but can you draw a line through it? Does it have such a, and sometimes it might be more flat. Sometimes it may be much more steep. So let me just quickly do one more thing to show you. If I use the scatter, and instead of the math anxiety, let me go back and put GPA in there, run that. Here, and again, one thing I wanted to notice here, you notice this is a negative, so you got a slope that's going negative. Again, we said the higher score on math anxiety, the lower the score on the final exam. In this case, as we saw, it was a positive relationship. It's going up. The slope is going up positively. As GPA goes up, score on the final exam goes up. You can kind of see if I was going to draw a line there, or I can just double click, add the line, close out of it, back to my, and here you have a straight line. So we can say that there is a linear relationship. So that would be an important step. I showed you here at the end, but you don't need it for correlation. So when you do the correlations up here, you don't need that. But when you get ready to do linear regression, anytime you're going to use regression, you have to look at the relationships between the independent variable and dependent variable to make sure there actually is a linear relationship. If there's not, you can't use the types of regression that we're talking about. There are ways to do it, which are beyond the scope of what we talk about in this class. But you need to make sure that there actually is a linear relationship. And so you're gonna want to make sure you run those and save those, as part of, the analyses and part of what you're going to submit for the assignment here. But this is how you do it. So multiple regression, 2 independent variables. There could be more. In some cases, there might be 3, 4. Simple linear regression is just going to involve 1 independent variable. And then again, these are the scatter plots that tell us whether the relationship is linear or not. And that's how you do correlation, simple linear regression, and multiple regression.